Hello everyone, I am Gönül. Actually, I'm a PhD candidate at Boğaziçi University in Istanbul, and now I'm a visiting PhD researcher at Utrecht University. And my advisor is Arjun Özgür and co-advisor is Pınar Yolun. And in this talk, I will share a Gandalf message about sharing privacy. So let's assume that Frodo wants to share a content in his online social network accounts. What kind of content? Let's think that this content can be an image of a ring, but Gandalf doesn't think that this is a great idea. Why? Because maybe this sharing action can have some catastrophic consequences. Like if Frodo shares this image in his online social network account, and then maybe his life will be in danger. Because maybe there are some bad people or some evil eyes desire this ring. So online social networks enable users to share content online with others. But in this case, users need to manage their privacy while sharing activity. And these kind of activities require more efforts to detect, to observe elements that the content contains. And these are time-consuming and error-prone. So we need to have a system that recommends privacy labels instead of a user and accurately. And in literature, most of the existing approach are centralized, which means that they use the data which has shared by many users. And one important aspect of the privacy is subjectivity. So a content can be identified as a private by certain individuals, but others do not think that this is a private content. So we need a subjective approach. We need this kind of approach. And we do not have access all of people's data, but always I have access my own data. So we need to have a system to preserve our privacy that recommends privacy labels for a given content by learning its users' privacy preferences, and then warn its user whether the content is public or private. So we propose an approach which is PESH, Privacy Estimation from Short History. It's agent-based approach, which means that each of the online social network users is represented by an agent, and PESH can access on the user's data, and when the system relies on only small data set, I mean if the system uses only users' data, which means that it uses small data set while classifying content in machine learning. This is better than a centralized approach because we need to preserve privacy of online social network users, and we have only access to the user's data. So our aim is we are trying to predict labels of a new image. For this task, we make use of TFRF, term frequency, relevance frequency method. I think TF-IDF is more popular one. Maybe you are familiar with TF-IDF. It is a sister of brother of TF-IDF. It's TFRF. We use TFRF because we care about the frequency of tags. I will mention about tags. Frequency of tags in public and private images. I mean, we use term frequency, relevance frequency method, and in this method, in our system, each image has 20 different tags, which are descriptive tags about images, Tags are constructed by users or generated by tools like Clarifai. So in this approach, we have images and we have 20 different tags for each image, which are describe these images. And in this formula, we have, actually, basically, we have some terms like R, S, and TF. These denotes basically the number of occurrences of a selected tag in all images, in all public images, in all private images. And then other term counts the number of occurrences of a selected tag in a specific image. So the benefit of this method is like you have public images, you have private images, and you have tags for each images, and you prepare your input for the classifier using this method. How? Using this formula, and I will show a sample scenario after this slide. And then, yes, in here you count the number of occurrences in public and private images, in the relevant images. And, yes, yeah. And these are the popular vector representations. Actually, we have image, we have tags for images, and we can use TFRF method to represent images as a vector, or we can also use vector representations like word embedding methods to create a vector to represent images as a vector format. Like each tag, using these word embedding methods, you can also have a vector representation for each tag, and then you can combine tags for each image. And in here, we have bird in the literature. We have bird embedding, word to vec, sorry, and glow. And using these word embedding methods, actually we can create feature vectors, feature vectors, and then use them as an input for the classifier. And since the learning is done, maybe some tags has not seen in the training phase, at the training phase. In this case, we do not have any representation for unseen tags. So in PESH, we propose similar tags using cosine similarity metric. It means if the tag has not seen in the training phase, but we have in the test phase, we find the most similar tag for this unseen tag based on a cosine similarity metric. So this is a sample scenario. Let's assume that we have 3 different online social network users, like on the left side, and then in this method, in this proposed approach, actual PESH, we have a software agent for each of the user. And let's say one of our users has 3 different images, and these images have 4 tags in this sample scenario. Okay, let's say one of user has 3 different images, and all of the 3 images has 5 different tags, and the agent of the user can reach these images, it's their labels and tags. So this agent knows everything about its users. User shares every information with the agent. And then this user has 2 new images, and tags are, you have shown the tags in this slide. And in the previous images, we have adult, child, fun, one, something like these tags. But in here, we have girl tag, And this tag has not seen in previous images, so this is new for us. Yeah, this is new for that agent. So using PESH, we can recommend the most similar tag with the girl tag, which is woman, using cosine similarity metric. And these are the matrices, actually inputs for the machine learning classifier for this example. Actually, we have 5 images in here. 3 of them are for training phase. 2 of them are for the test phase. And in here, we construct, actually at this step, we count the number of occurrences that tag occurs in the public and private images. Columns correspond to the tags, like we have adult, child, concert, blah, 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 woman. And rows correspond to the images. We have 5 images, so we have 5 rows. And at the bottom, we construct matrices using public images. I mean, adult, yeah, the first image in the matrix 1-1 index, the first image has adult tag, and adult tag occurs only one time in public images, so the cell value, the index is the 1, and you can use the same logic to complete all of the cells of the matrix, and this one is for this one keeps the occurrences among the private images, and then using TFRF formula, we calculate the weight of tags. Actually, we assign weight value using TFRF method to each tag, and tags are represent the images. Yeah. We use a subset of pick-alert dataset. Pick-alert dataset consists of flicker images on various topics, and which are labeled as public or private by external viewers. And in here, actually, you have shown an example for public and private classes. On the left side, you show the public class example, and this one is for private class. And you show the 20 different tags for each images. And these are really descriptive. And these tags are created using by Clarifai app. Yes, in our simulation, we have 59 agents. And as a classifier, as a learning algorithm, we use random forest with 100 estimators. We have epsilon value. Actually, in TFRF formula, in the previous TFRF formula, in the original one, we do not have epsilon value. But if the tag does not occur in public or private classes, so we have a division by 0 problem. So we add epsilon value, which is very close to 0. And we have cosine similarity threshold because we can recommend a tag for unseen tags, and we can define the threshold value for the similarity. I mean, if the similarity of the tags bigger than 0.7, yes, it's very similar for me. So you can recommend this tag to the unseen tag. Yeah, and we execute our scripts 10 times and take the average of the results. Yeah, I use Python as well, as expected. Yeah, I really like Python. These are the libraries: Pandas, NumPy, scikit-learn, Pickle, Math, Random System, NLTK. For word embeddings, we have bird embedding library. And if you want to use TF-IDF model, you can use GANSIM and so on. I also use Matplotlib, but I forget to add this. Yeah, so you can use these libraries for this work, or you can code it yourself. I don't know. And I pick some results for this approach for the performance for showing the performance of the our proposed approach page. Yes, we can prepare inputs using word embedding methods like BERT, GLOB, or word2vec, or we use TFRF method to assign a weight value for text. And if we recommend a tag for the unseen text, this is page. So you can show the performance of the of different approach in here. Out of the if we do not recommend any tags for the unseen tag, the performance is very similar, is the same actually for the accuracy metric. GLOW, word2vec, and TFRF. But if we recommend a new tag, not new. If we recommend a tag from our training data set for the unseen tag, the performance is increasing for all of the metrics. And this is another, we rank the tags in the frequency of relevant classes, like public and private classes. So yellow ones are for public class, and blue ones are for private class. You show the most frequently used tags on the x-axis, and you show the frequency of the tags on the y-axis. So I think this is important for me because, I really like this result because when we look at this result, we show that people tag is more frequently used in the public classes, but actually these are the most frequently used tags, but most frequently used tags for public and private classes. So these are common tags for our classes. And people is used in private classes more than public classes, but it's very common tag for both classes. And like for women, it's also like a private class tags because the ratio of the private class and public class is, the difference is huge for the woman tag. And yes, some tags are more frequently used in a relevant class. So this shows this difference, this similarity, or this information. Actually, this is a work, and we published a workshop paper in AI for Privacy workshop. So if you want to get more information about this work, you can scan this code and go to website and find the PDF version of the whole work. That's all for my presentation. If you have any questions or comments or feedbacks, I would like to answer all of them. Thank you for listening.
Thank you for your talk. And we have one question online, and then I'll give it again to the room.
Okay.
2 questions.
Okay.
Instead of replacing singleton tags with its closest one, wouldn't it be possible to sum the embeddings of all terms in a PIC to get a feature vector?
Can you repeat your question after the okay, can you repeat your question?
Yes. Instead of replacing singleton tags with its closest one, wouldn't it be possible to sum the embeddings of all terms in a PIC to get a feature vector?
For the tag, or I don't get the point.
Is this question out of? Is this your? Okay, then I'll give you the mic.
Yeah, actually, You can do this. Hi.
Thanks for the talk. Great talk. So the second question was also mine. So how do you?
Okay, sorry.
Maybe this should have been the first question. So how do you compute the feature representation using large language models?
Using?
Large language models. So you compare your baselines are BERT and.
Yes, word embedding methods.
Yeah, exactly.
Yes.
Where was that?
Uh-huh.
But then you have this this table, right? Where
Yes.
you showed the metrics of the other.
Performance.
Yeah, that one. Yeah, okay. So when you use these approaches, how do you compute the feature vectors for your pictures?
So yeah, we have an image. We have 20 different tags, and each tag can, we have a vector representation for each tag using word embedding methods. Like one of them, like glow, has 200 dimensional vector, or bird has different dimensional vector. So we have feature vectors, and then we can combine, we combine 20 different vectors to get only one feature vector for each image. Yes.
Okay, so you're assuming the vectors.
Yeah.
Okay, that was the question. Yeah. Okay, perfect. Thanks.
Okay, second question. What does the name PESH stand for?
Yes, is privacy estimation from short history. Because we only use users' data, so we have small data set, and we only use the past experiences. We only learn features or learn sharing behaviors, only users' past experiences. So we use short history, and yeah.
Okay, any question from the audience in the room? First you, then I come to you.
Yes, my question, thank you for your presentation. Yes, my question is, do you recommend a privacy or a public tag? But you said at the beginning that it has a subjective point of view. So has the user a last will to say, okay, yeah, the PESH has recommended me to tag this photo as private, but I think it's a public one, so I would like to learn. I mean, is there a feedback loop where it
Right
learns?
now, no. But it would be a great idea. Yeah, it would be nice.
Okay, thank you.
Capable of this thing. Yeah, right now we do not have any feedback mechanism like this, but in the future, yes. Thank you.
Hi. So
Hi.
yeah, great talk again. It was really, really interesting. From that table with the results, with the precision F1 and recall and accuracy, I'm surprised that BERT got the lowest results there, given that it's, if you into NLP, it's like that thing that everybody should be using, right? So I was curious, how exactly did you use BERT in this? Because BERT provides like vectors with a context, right, given a sentence.
Yes.
But did you apply it like on a single word and then use that vector? Or did you provide like a chunk of words or tags, I don't know exactly how you use it, to get those vectors? Because if you use glove or word to vec, etc., like it doesn't have context. So I'm very surprised by the results.
Yes. Actually, yeah, thank you. That's a very great question. I use, for BERT, I use this one, which, yeah, I use BERT model, word embedding model, who's trained on contextualized version, and you can reach this from this. So the result, I think, the result depends on the pre-trained models. I mean, for the second one, I use a model who trained on the Google News corpus. Actually, none of them are trained on private news or private documents. So the performance of the bird to wake glow depends, based on their pre-trained documents. So bird yields very great performance and yields better performance other popular methods in literature. And when I use this version, contextualized word embedding model, so I can get the result on the table. So it depends on the pre-trained documents.
Any more questions? We have enough time for questions. I don't see anyone raising their hand, so I think we're done. Thank you again for your presentation, for answering questions, and thank you for being here, and have fun at lunch.
Thank you.